How's it going, guys? In this video here we're going to talk about how a power inverter works, and we're going to start off with low frequency, and then we're going to go to high frequency, and then we'll go back to low frequency. You'll see why in this video. To start off, we're going to go back to, I don't know, 1970s we'll say, and how power inverters back then was made pretty simple. And a lot of it had to do with the fact that the type of loads you'd be running on it would be like corded power tools that has brushes, circular saws, or cordless, or not cordless drills, but corded drills that has brushes, or incandescent bulbs. The first power inverters or low frequency, and they kind of look like a battery charger, to charge your car up. Car battery up. Inside of them you would have found a ginormous transformer like this one. This thing's probably a good 10-12 pounds, and it was a step-up transformer. Basically step it up probably about 10 times, or maybe a couple more. We'll call it 10 times. That's pretty much what you get at the end of the line on most inverters, but depending on if it's sine wave or modified sine wave, or this one we're going to talk about, square wave, we'll go with 10 times. Basically you have a primary and a secondary winding, and whenever your primary goes in, you get 10 times that out voltage wise. Now a transformer has to have alternating current. Has to. That's how it works. So you have to create a sine wave, or at least a square wave, for a transformer to function. It cannot boost DC. So your DC on this, this simple inverter, DC comes in, then you're going to have a heat sink with some transistors, and I also even kind of made them look dated as far as they're like little canister. I don't know what package they call those. TO3 somethings. But anyways, and then you're going to have some simple driver board that has, basically some kind of IC on it. Probably back then it would have been some ginormous thing. And some free driver, like, TO92s or TO220s. Free drivers to drive these, and it's going to keep pulling it to ground, back and forth, creating a square wave. So that's pretty much it. DC comes in, these devices right here turns it into a square wave, and then you get your 120 volts out. The only thing about it is low frequency requires a giant transformer, and even then a transformer this big might only be good for 500-600 watts, just because of the frequency that it runs on. So then you go to high frequency, and a transformer, this is a little exaggerated, but a transformer this big can do the same job as this ginormous one at a higher frequency. You turn, instead of doing 60 hertz, you pick it up to a kilohertz or more, and this little guy right here basically is, in a sense, overdriven. Best way to describe it, by frequency, so you can get just as much through this, or just as much current through this thing as you do this one, just by increasing the frequency that it runs on. Alright, so here we have this is a pure sine wave inverter. It's 1500 watts. I did a previous review on it, but we're going to use this as a demonstration. Now, a modified sine wave and a sine wave inverter, there isn't a whole lot of difference. You got some chokes and things right here for filtering. Your oscillator is going to produce through different steps. It'll have like different steps building up to the sine wave that you see. But if you was to blow it up big enough, you would actually see little ripples in it. because there's actually several different frequencies built up to produce that sine wave. But anyways, we're going to start at the beginning with this. Since you have high frequency, the DC comes in, goes through these caps. So, you get a certain amount of storage in these capacitors right here. One leg is going to go through the transistors, basically the same as what you had over here. But instead of this oscillator being 60 hertz, it's going to be, a kilohertz, or it can be whatever. It can be whatever at this point. It doesn't really matter. The higher it is, the smaller transformers can be. I often complain about the size of transformers or the limited amount of transformers in an inverter. Particularly, I like seeing at least, for every 500 watts an inverter is, I like seeing a transformer. It's just it seems like a good number. If one of these transformers is has to do, say, 800 watts each, it seems like inverters like that get fidgety and oftentimes burn out transistors over here, because you get like this saturation issue, getting that much current through a small device. Once you get to a certain point, there's a saturation problem, and then the inverter will be just running, and then all of a sudden, boom, for no given reason at all, it'll blow out a transistor. And that's why I always complain about the size of them or the limited amount. Like this one machine here is 2,000 watts. Sorry, it's 2,000 watt. I'd like to see 4 of them in here for that, but this machine seems to be doing pretty good. I think a lot of it has to do with the fact that it does have good branded components in it. They're just not some generic things. But anyway, back to the story. Power comes in, gets stored in these caps, and then one leg is going to go through your transistor right here, pulling these to ground, creating a frequency. And then that is high voltage alternating current, and it's probably a square wave. It's probably a square wave like that, but the thing about it is it's such a high frequency, you don't get the buzz effect. You're not going to really hear these guys buzzing because the frequency is so high. It's probably a square wave like that. Now, that high voltage alternating current goes off to these transistors, or not transistors, but diodes right here, and gets rectified to DC. So this is building a bridge rectifier right here. So then you have high voltage DC. They get stored in these caps right here. Then these transistors right here turns it back into 60 hertz, 120 volts. Or given it, you got a different, in a different country where you're 240 volts, whatever. That makes a whole different aspect. Is the boost stage is different. The whole aspect's the same. Your boost stage is going to be higher, and then your output and everything will be different. But the same principles across the board here. But that's pretty much how it works. These capacitors right here are very important in the setup. They help with power regulation when you turn on heavy loads. You notice that you don't have it gives the machine a chance to keep the power at a steady level. These capacitors right here, for the input side of it, just as soon as the power comes in and gets stored in these caps, these capacitors really don't have a whole lot of importance to them. I've actually seen quite a few inverters that doesn't have any caps. They'll have caps for right here, but none right here. I mean, essentially your battery is a giant capacitor, and you have to have a lot of battery to run something like this. So they do help a little bit, like with sudden loads and things. There is a little bit of a buffer with these capacitors, but they don't really have a whole lot of importance. These ones right here definitely do. The bigger these capacitors are, generally the better the inverter performs. Alright, so now we're going to go back to low frequency again. We'll get this ginormous transformer back up here. Alright, now let's just say we remove those little transformers right there, and we stick this big massive guy down on there. Just have this one big massive guy, but instead of running, you know, this thing doing everything all on its own, where it's just running at 60 hertz and it is your output. Instead, you're still going to have all this stuff here in the front. So now you could say run this at 200 hertz. Okay, run it at 200 hertz or 300 hertz. You can still call that low frequency. So, you know, then you send it off over to these diodes, and you still have the same effect coming out here. But you have a low frequency inverter. Granted, it's not 60 hertz, but it could be a few hundred hertz, and you're not going to have as much RF coming off the unit and bothering radios and things, because it's just a few hundred hertz, not, you know, a couple thousand or 1,000 hertz. So that's pretty much the only difference, really. Like, the modern day low frequency inverters are going to have a big transformer, and now since you're also running this at several, you know, a couple hundred hertz, this transformer now can do, you know, instead of, you know, 500 watt that I said before, it can do a couple thousand or even 5,000 watts and only run it at a few hundred hertz. So anyways, that's about all I got for this. I mean, it's pretty much the basics of you know, everything else you see down in here. You know, like this board right here probably produces the the sine wave that you need. You know, is controlling these transistors right here. You know, all the other smaller components you see here are going to be drivers and such for these guys. You know, but that's pretty much it. I'll catch you guys later.